I'm Peter Thornycroft with HPE Aruba, and my colleague over here is the very expert Sam McMullen with Federated Wireless. He's going to do the tricky bits. I'm going to get you warmed up for him, maybe. So we're here to talk about 6 gigahertz. As you know, the 6 gigahertz band is actually 1200 megahertz, 5925, 7125. I'm going to talk mostly about the US here, because that's where we're doing the most work. But it is coming to, we hope, pretty much every country around the world. And I'm sure you've seen slides about that. The AFC is not applicable to everything we do in 6 gigahertz, but it is applicable to large parts of it. And we think that also will be replicated across different jurisdictions. So what you see here right now is US-centric, but you will probably see this going out worldwide over the next few years. So the special thing about 6 gigahertz that requires the AFC is the incumbents. Right? There are people who were there before, they're licensed, they're allowed to transmit. Mostly we're talking about fixed links, point-to-point microwave. And when we go into 6 gigahertz, we're doing dynamic spectrum sharing. We're not allowed, for very good reasons, obviously, to interfere with these incumbents. We cannot cause harmful interference. And that's really the reason why we have the AFC. So when we go into 6 gigahertz, there are 3 classes of device. The one on the left there is called LPI, low power indoor. So this has a few stipulations. It's indoor, can't be weatherized, can't have antenna connectors. We're talking about APs here, and not battery powered. And you can only transmit under those conditions up to 18 dBm in a 20 megahertz channel. It's all done by power spectral density, so the different channels have different dBm. We'll see that later. So that's low power indoor. If you're doing anything above low power indoor, maybe you're outdoors, or you want to go higher power, or you're weatherized, or all the rest of it, then you need to talk to the AFC, the Automated Frequency Coordination System. And that's where standard power comes in. So sort of by definition, everything that's not LPI and is above it, as it were, you're in standard power and you need the AFC. And the very low power is not concerning us today, so I'm not going to go into it. So this AFC thing in that tasteful sand color on the slide is a server in the cloud. There's a defined API to talk to it from the AP. That's defined by the Wi-Fi Alliance. It's pretty simple. I'll show you later. So when an access point comes up and wants to start transmitting, it has to ask the AFC, where can I transmit, what channels and what powers? And that's pretty much what we're talking about here. So the AP has to tell the AFC its location. It can also sort of talk about what channels it really wants and some power levels. But the important thing is the location. And then the AFC will come back and say, well, this is what you can do at that location. That's what we're talking about. And to talk some more about it, here's Sam. He's going to talk about what goes on inside the AFC when that query reaches it. Down arrow.
Thanks, Peter. So as Peter mentioned, once a day, Thought it went on. Oh, there it goes.
Okay.
Sorry about that. Okay. So once a day, as Peter mentioned, an access point that wants to operate using 6 gigahertz standard power needs to communicate with an AFC. And as Peter mentioned, it needs to provide the AFC with its location as well as its location uncertainty, and also an FCC ID and a serial number. And that's our AFC uses the Wi-Fi Alliance standard device interface to transfer that information. On top of that, we also have the device give us a bearer token for additional security. So assuming that the bearer token checks, then the AFC goes and checks with the FCC to make sure that the device is authorized. If so, then the AFC goes and does all the spectrum availability calculations. So those calculations, first of all, they rely on an incumbent database that we get from the FCC. And we do a synchronization with the FCC once a day as well. And we also need data from Canada. So we also have to go and get data from ICED in terms of their incumbents. And there's about 100,000 total incumbents. The AFC also, for doing its calculations, needs some geodata. That's terrain, clutter, building data, as well as some antenna data that it uses for its calculation. So it takes all that information, does the calculations, and then replies back over to the device. Oops. So in effect, the AFC, what it does is it computes a protection contour around each of the incumbent receivers, the fixed service receivers. So if an access point is outside of that protection contour, then this particular incumbent won't constrain its spectrum availability. But if it's inside, then depending on its location, it'll be constrained by a certain amount in its power. So in particular, if it's close to the receiver, and perhaps in its bore site, it's going to be constrained the most, and that's shown here by red, the red points. Whereas if it's kind of out towards the edge of the contour, it may not be that much constrained, maybe 2 or 3 dB, and that's shown by the blue points. So the heat map that I was showing there, what we do in our calculation is we divide space into a fixed grid, where the grid is defined by 1 arcsecond pixels, 1 arcsecond by 1 arcsecond pixels, and an arcsecond is about 30 meters. So in each one of those pixels, we determine the maximum power spectrum density that a device could operate, so as to not cause interference in excess of an I over N interference to noise threshold of -6 dB. And that's the specification that we got from the FCC in terms of the protection criteria. So with that, then we can go, and for each one of those bins, we assume that the device is located in the middle of that bin, and we compute the maximum power that it could operate. That would give a -6 dB, and that's shown by the equation here. So it depends on the noise in 1 megahertz, the noise figure, the -6, which is that I over N, propagation loss, the gain of the antenna, the incumbent antenna in the direction of that point, and some feeder loss. So we do this calculation for all points around the incumbent receiver. When we get the request from the device, it'll have an uncertainty region. So we'll look at all the points that are inside of that uncertainty region and pick the smallest value in there. So for example, in this case, the smallest value inside of that uncertainty region is 6. So that'll be the power spectrum density that we use for those frequencies corresponding to that incumbent for this particular AP. So I'll show you on the next slide then how it kind of glues all together. So in this example, a particular device is inside 8 protection contours, so 8 incumbents. So we need to look at each of those 8 incumbents and figure out the overall spectrum availability. So the one all the way on the left, the device is such that when I look at that fixed grid, it's going to cause a 20. So the power that we can offer it so that it won't cause excess interference to that incumbent is 20 dBm per megahertz. And then you can see, based on the response at the bottom, that over the frequency range corresponding to that incumbent, which is 6078 to 6109, that we can reply back with 20 dB, 20 dBm per megahertz, and that's the power level that that device could go if it wanted to operate on those frequencies. So continuing on, another incumbent imposes a constraint of 11 over 6710 to 6740. So you see that kind of a little bit higher up, where you see an 11 in terms of the frequencies. So that's basically how we compute. For every device that comes in, we look at the protection contours, figure out what is the, what power can that operate on so as to not interfere with the incumbent, that particular incumbent, and then glue it all together across all frequencies. So just one other thing that the AFC has to take into consideration. So most of it is the 100,000 or so incumbent fixed service receivers that we have to protect. There are also a handful of radio astronomy sites that need protected. Most of these are in rural areas, so they, in most cases they won't come into play. But if you are inside of one of these areas that's shown on the map, there could be 25 megahertz that would be unavailable because of these radio astronomy sites. Okay, so I wanted to just go a little bit deeper into that propagation loss calculation that's needed to get the power spectrum density. So for this, the FCC mandates that all AFCs use the irregular terrain model when the distance between the device and the incumbent is greater than 1 kilometer. Though the FCC basically left it to industry to work out kind of the parameters that would be used with the irregular terrain model. So what ended up getting worked out was we'll use some models for climate zone, surface refractivity from the ITU. We'll take elevation data with 1 arcsecond resolution and some parameters that were worked out within the standards bodies. Most notably, you'll see here, if you know ITM, we're using a confidence of 5% and a reliability of 20. So we went with a pretty conservative set. That was at the insistence of incumbents, so that's why we ended up with that. But that's what the AFC uses for the distance greater than 1 kilometer. One thing I did want to note about the ITM is it's really good for modeling propagation loss over terrain, but not so good at accounting for clutter. That's clutter from buildings, trees, whatnot. So to augment the ITM, the FCC allows for us to add some additional clutter loss, and the clutter loss that we apply is based on the land category at the location of the device. So if it's rural, the land cover, and we get that from the USGS NLC database, then we'll use P.452, whereas if it's urban or suburban, we'll use P.2108. And I won't go over this in super detail, but if the distance is less than 1 kilometer down to 30 meters, we'll use winter 2 for propagation. And again, we'll use that land category to determine which one of the scenarios from winter 2 to use in the modeling. One thing that is different between AFCs is the FCC allows us to use site information in determining whether the path is line of sight or non-line of sight. So if we can determine based on some building data that there's an obstruction in the path, then we can use the non-line of sight version of winter 2, which typically ends up being maybe 6-8 dB difference. If we don't know that, then we have to use a probabilistic model in the modeling. So it's definitely in the benefit for spectrum availability if we make use of that building information. Okay, so that's what I have in terms of describing AFC. I don't have time. We're going to go now do a demo. I don't have time to also show the dashboard that goes along with this demo, but I did want to put a plug in for it. So Federated has a dashboard where you can see for all requests, all of the incumbent contours that cause the spectrum availability that come back in the request. And Peter's going to show a location a little bit to the west of Flagstaff, where I think there's like 8 incumbents, and you can see all of the contours here. And what you could do on the dashboard is you could kind of go one by one and see, why is this frequency being excluded, and you can see it on the map, which incumbent is causing the constraint. But with that, I'll turn it back over to Peter.
Cool. Put my specs on and change the screen. Get out of that. And we go into that. Ah, so much for that. That's Am I on the right SID there, WLPC? Yeah? Well, let's try them again. Ha! It's teasing us. Okay, so this is a tool that we've put together in Aruba. Unfortunately, we can't let it outside the company, but I think you'll find that many other companies will be making something similar, because this is a very common sort of thing you want to do. It's a client device. This one's on Android. I've got it on macOS, iOS. And it runs the API defined by the Wi-Fi Alliance for AFC. So you've got the inputs, and you get the outputs, and you can see what's going on. So let me just describe. I apologize, you probably can't see very well at the back there, but I'll talk through what we've got. On the left here, these are inputs, essentially things that get sent to the AFC. The label doesn't, that's my label. You can send desired power. It doesn't actually do very much. It just means the AFC doesn't send you back anything that's below that power. There's a location uncertainty which goes with the location. So the location under the map here is lat long. So you send up a lat and a long. And then there's actually an area that goes with that. And that can be an ellipse. We simplify the ellipse to a circle because, well, it's simple. You can also make polygons, radial or linear, different shapes, and that's the uncertainty associated with your location. So you end up with this sort of area in which the transmitter might be, and when that goes to the AFC, they find the worst possible spot in that area. So that's where the location uncertainty comes in. You put the antenna height up, and then there's an uncertainty that just adds to that, because that's the worst case. And then we can say indoor, outdoor. Okay? So those are the inputs. There's also stuff that I haven't really shown here. There's the FCC ID goes up and some things like that. I have a little log here. Let's have a look. Again, apologies if you can't read it all. It's JSON. It's pretty simple. At the top here, we've got the query. And it's got the stuff I talked about. I'm asking for both the spectrum response, which gives you that power spectral density, and a channel response, and I'm asking for all the possible channels in this case. You don't have to do it that way, but at the moment, there seems to be no cost associated with it. So on the display at the top, you can see that top green line is power spectral density. You can't quite see it, but most of it's 23 dBm per megahertz, and if we multiply that up, in 1 megahertz, it's 23. So in 10 megahertz, it's 33. So in 20 megahertz, it's 36. I think. And in fact, the ceiling is 36. So everything is giving us back here. In this case, because I'm near the San Jose airport, but I'm only 3 meters off the ground, is coming back like that. Let's go to where Sam was showing us, which is a little bit north of here in the middle of nowhere. Punch it up, cross your fingers. Okay, we got something back. What we got back was essentially clear. That means we can do anything we like here indoors. I'm going to change it to outdoors. And you can see over on the left there, we've got some notches in that power spectral density, which is because that's where those fixed service incumbents might be impacted. So the AFC says we've got to drop our power. And the PSD should correspond as you go down to the 2040, 80, 160 meg channels. And they go 3 dBs each, because the way the FCC regulates this is by a power spectral density. So as you double the channel width, you get 3 dB more. It actually keeps the SNR constant, which is a nice thing. So you can see maybe under the 11, just above the 6200, there's 11 dBm per megahertz. That goes to 24 dBm for the 20 megahertz channel, 27 dBm for the 40, 30 dBm for the 80 megahertz channel, and 33 for the 160 megahertz channel. We can move again if we like, and go to, oops, no, let's go to, come back. Here we go. As far as I could figure out, this is our hotel. So let's see what we could do here. I'm looking indoors, 3 meter antenna height. You can get everything you want. If we go outdoors, there's a tiny little notch up there you can see around 6600. Let's go up to 30 meters antenna height. Oh, there's quite a lot about. So we'd have to be careful there. And this is where whatever logic your AP vendor supplies will pick the best channel. And then if we really want to go out a little bit further, this stresses the AFC a little bit, but I'm going to go to a kilometer radius. It may take a little longer to think about it. It did come back for me earlier. There we go. So you can see there are some places you pretty much can't get anything. Oh, something I did want to mention, you don't use AFC across the whole of the band. I think it's Uni 5, Uni 7. So down the middle there, there's that white area. You can't transmit there anyway. And up on the right, the Uni 8. I believe that's because there are mobile transmitters out there, incumbents, and AFC can't help us with mobile incumbents. Okay, very quickly to finish up. So from the AP point of view, you've got to figure out where you are. These were in case the demo didn't work. I can go over those. So we're going to need to figure out where the AP is. GPS is the most obvious thing to do that. I think every vendor will work things out there for their outdoor APs in 6 gigahertz. Aruba, my company, wraps this into the Open Locate framework, which does a whole lot of other stuff too. But you need to get a location out of the AP somehow. Our good marketing people asked me to put out a few leads. The top one there, Aruba leads the way, is a little bit of a boast, I think. But it is the great Chuck Lukaszewski, so well worth your time watching Chuck. And thank you. I think we got some time for questions.
No, we don't usually do questions. Does anybody have a question for Peter? Jason.
Thanks. For those of us who are old school and like to do static channel and power plants, given that these are fixed wireless systems, right, the data is not like, I mean, even though the APs have to check in once a day and validate it, it's not like this data changes a lot over an extended period of time. So is there viability in actually incorporating this into our design tools so that if I were, say, designing to upgrade the Wi-Fi at this hotel for 6 gigahertz, which needs a bunch of outdoor APs, you know, I know what channels I can viably use and what channels I viably can't at the design phase, so I can say, okay, this is how I want my 6 gigahertz channel layout to be. And then, obviously, if the APs have to go in and check and revalidate that, that's fine. But I personally would want to plan all my 6 gigahertz channels out.
I think that's a viable, generally viable scheme. Sam, I think we talked earlier about how often these things change.
Sure. So we've been tracking this for the last couple of years. 2 years ago, 3 years ago, there were 100,000 incumbents. Now there's 108,000, which means in a given day, there's maybe 10 or 12 that change. So your chances, so you may be affected once you have an assignment, but chances are really low that you would be affected because of those stats. And by the way, Federated Wireless, for one, we can also provide you with some planning tools. So, if you want to go in ahead of time and see what the spectrum availability is in a certain region, you can use planning tools for that, and without actually having a real device with an FCC ID. So it's pretty stable, and we can definitely help with planning.
All right, thank you very much.